Okay, so this video is to explain sort of key sort of chemical theory behind the experiments that you're using and other experiments as well, because sort of understanding some of this theory will help you understand what you're doing in experiments, but also will help you understand what to do if you encounter any problems or issues, because you'll be able to use the theory to kind of work out how to fix and correct them. So relating to the iron experiment, the key sort of theory that I'm going to cover, it relates to solubility and the solvents that you're using, and then a key sort of application of solvents and solubility are through the techniques of recrystallization and hot filtration in terms of how they work. Okay, so solvents are basically the workhorse chemicals of the lab. You use them in almost every experiment that you do, and what their purpose is they're there to sort of dissolve your chemicals, your reagents that you're reacting and mixing together. You use them to help you purify your samples and transfer them from fast to flask. Okay, so when you're using solvents, what you're trying to do is you're trying to sort of make sure you can dissolve your chemicals, and so when you're using certain solvents in the lab, the reason you're using them in your particular experiments or stages of your experiments is because they are very good at dissolving the chemicals that you're using at the time. And so what I'm going to cover is what the structure of solvents are and how solubility works. Okay, so you can think about when things are dissolving or not dissolving for you, you can sort of think about why that's happening, what the structures of the solvents are and what they should be doing with respect to your chemicals, and you can sort of fix and correct any issues you might have. So what I have here are sort of the sort of key solvents that you sort of use in the lab, and they're sort of grouped together by the type of solvents that they are from their chemical structures. So we have polar protic solvents, so these are the alcohols, sort of water, methanol and ethanol. Okay, so they're polar because they've got that polar OH bond, and they can also donate a hydrogen through acid-base reactions. Then we have polar aprotic solvents, so these are got electronegative sort of bonds, but they don't have the hydrogens to sort of donate or accept hydrogens in acid-base reactions. And then we've got other sort of standard organic solvents as well, dichloromethane, ethyl acetate, which kind of have some sort of polar bonds, they're not as polar as the other polar aprotic solvents. And then also generally, as we get towards the other scale, and there's a scale, we've got solvents like toluene and petroleum ether, which are kind of mostly sort of carbon based, so no sort of real difference in the polarity between the bonds, so they're quite non-polar in their structure. Okay, and one of the key properties of a solvent, and the reason why you use it to dissolve up chemicals in the lab, is because they exhibit certain polarity. So there's a key sort of theory, like dissolved like, you need a solvent which matches the polarity of the compounds that you're trying to dissolve for it to dissolve it. And then the other thing you need to think about with solvents as well, again, it's to do with their structure. So always think about the structure of the solvents and what properties, how that leads to the properties that they have. So solvents like the alcohols, like water and methanol, for example, they can hydrogen bond, and whereas some of those non-polar solvents like petroleum ether have van der Waals interactions, but very poor at sort of hydrogen bonding. So what can happen with solvents is that certain solvents can mix together, such as the ones which can hydrogen bond, like water and aqueous solvents can mix together, but the non-polar organic solvents don't mix with the likes of water, and so they separate out into different layers. And again, there are certain techniques that you're going to learn in your course where getting solvents to separate out into different layers is actually really important and key in terms of how they work, and getting compounds to dissolve in the aqueous or the organic non-polar solvents, it is quite important for you to be able to purify them as well. Okay, so just to appreciate that, being able to sort of hydrogen bond or having not hydrogen bonding is quite key for why certain solvents will mix or not mix together in the lab. So as I kind of mentioned before, one of the key sort of principles for getting a compound to dissolve is this principle of like dissolves like. So what you're trying to do is you're trying to get your compounds to dissolve in a solvent. You need to think about the structure of the chemical that you're using, and then you need to think about the chemical structures of the solvents as well, and pick one that matches pick a solvent that sort of matches and aligns with your chemical structure. So if you have a non-polar molecule that you're trying to dissolve, then these are the types of solvents that they will dissolve in, these sort of non-polar organic solvents. So they'll have that sort of van der Waals type interactions between the molecules, so they'll happily mix together. If you've got a molecule that's a bit more polar, so we introduce some oxygens in here, so we've got some electronegativity, so we've got some more polar bonds, then there's this whole host of solvents that this type of compound can dissolve in, ranging from diethyl ether to methanol, because they've all got kind of an organic sort of component to them. So this is actually the structure of the third compound that you make in the iron experiment, the red compound. Okay, so it's a neutral molecule, but it's polar, so it will dissolve in most of the organic solvents which have some polar bonds in them. But it will dissolve poorly in the non-polar solvents, and it also will dissolve poorly in the likes of water as well, because water is too polar. And then here I've got the structure of the potassium oxalate salt that you make in the second step of the iron reaction, and this is a salt. Okay, so it's different in its structure to the other iron compound. It's a salt rather than it being a neutral molecule, and that completely changes its solubility as well, because salts will dissolve in very polar protic and aprotic solvents like water, methanol and ethanol, and won't dissolve very well in the other solvents. So actually what you do in the second step of the reaction is you have your reaction in water to make your iron potassium oxalate, but then you add more ethanol. So what you're doing is you're adding more of a less polar solvent, and that actually helps your potassium oxalate sort of precipitate out of the solution as your green crystals that you isolate in the end, because it has less of a solubility in the ethanol than it does in the water. Sorry, I should have also said that there are other factors as well that affect the solubility as well as polarity. How much solvent you use, the more solvent you use, the more likely it is that it will you will dissolve your compound as well. So increasing and adding solvent will help to dissolve your compounds, and also temperature is a factor as well. Some chemicals, if you pick the right solvent and compound mix, will be sort of soluble in hot solvent. Okay, if you increase the temperature, you increase the solubility, so it'll be soluble in hot solvent, but when you cool it down, it will precipitate out. Okay, and these sort of factors, sort of polarity, volume of solvents, so concentration, and temperature, underpin the technique of recrystallization that you use as one of your main ways of purifying your samples in your experiments. So what you do is you pick a solvent for your recrystallization that matches up with the compound you're trying to recrystallize in such a way that it has relatively good solubility. It has good solubility when the solvent is hot, but poor solubility when the solvent is cold. And so what you do is you sort of add. You have your sort of impure crude product. You add hot solvent to your crude product. That will dissolve up your impurities and your product. Okay, because the solvent is hot. It has good solubility in the hot solvent. Then you cool your solution down, and what will happen is your product starts to precipitate out because it's got poor solubility in cold solvent, but the impurities remain in the solution. So then when you filter your product, you will have pure product at the end of it. And because concentration and volume of solvent is also important and a factor in solubility, when you do a recrystallization, you do need to make sure you use the minimum amount of hot solvent as possible, because the more hot solvent that you add in to your recrystallization to get your crude to dissolve, the less product you'll get to precipitate out. So even if your compound has poor solubility in cold solvent, if you still have a lot of that solvent, you will still get some of that compound to dissolve, and you'll lose that product and you'll get a lower yield at the end of the reaction. Okay, so as I kind of mentioned this before, so I'll only cover this briefly now. In the second step of the reaction, you're making the potassium oxalate salt, and so water is a solvent. It dissolves your starting materials and reactants well, but then you add that ethanol, which salts have pure solubility in when the solvent is cold. It's quite good when it's hot, but it's poor when it's cold. So then it sort of crystallizes your iron oxalate out as green sort of crystals. And you're performing a hot filtration in the final step for the red iron compound at the end. So a hot filtration works pretty much like a recrystallization. You dissolve up the compound in impurities, most of the impurities. Methanol will be your solvent for this hot filtration, but there are also some insoluble impurities as well. So what you have to do is you dissolve up your compound and the soluble impurities in the hot methanol. Then you need to do a quick filtration with hot glassware with your compound still dissolved to remove the solid insoluble impurities, and then you cool your solution down just like with a regular recrystallization, and that should crystallize your final product at the end. Okay, so that's the summary of the sort of theory behind the iron experiment, and a general summary of the theory relating to solvents and solubility and how they work with relation to crystallization.